Welcome everybody to EE 512A, a course entitled Advanced Inference in Graphical Models, or so it says. My name is Professor Jeff Bilmes, and I will be your trusty, humble lecturer for this quarter. And there's a lot of interesting stuff that we will be doing. There's a lot of complicated things we will be doing, but hopefully also you will find that we will be doing a lot of useful things. So the first announcement I would like to make, of course, is to welcome everybody to the class and start going with what we're going to be doing. So this is the class is going to be held Monday and Wednesday. This is today's Monday in this room. In case anyone doesn't know where we are here in PACCAR 297. And for those of you who are in either EE or CS or statistics, obviously you might notice that this is not your building. This is the, I think this is the business building or the economics department's building. The reason why we are in this room as opposed to another building on campus is because they have much better facilities here, like, for example, windows in their classrooms. They also have working projectors in their classrooms. And also it gives us all an opportunity to get a little bit of walking in, and everybody should be aware of the benefits of walking. And if you are late for class, you can actually do some running. So you can run to class and not be late. So that's what I will probably be doing. So not only, as you've probably noticed, will the lectures be here in PACCAR, but the lectures will also be ultimately published on YouTube. I've done this before in the context of just an audio only lecture, but I've never done a video lecture like we're doing now. Although I did try once and everything crashed, so I don't know if it's going to work this time, but we'll see. If this thing doesn't crash, then you can watch these lectures and unfortunately or fortunately, depending on your perspective, give these lectures on YouTube. Now, why are we doing this on YouTube? Well, there's the purported reason, which is, it's pedagogical. It's a better pedagogical experience to be able to not only come to class but also review the material, especially because we're going to be going into some fairly in-depth technical detail, and being able to hear it again or listening to maybe a particularly funny joke or deep technical result again is better for pedagogical reasons. But the real reason why we're doing this is because I've become recently a narcissist, and so I like posting things, and hopefully I will become famous, and I will get many subscribers to my YouTube channel by lecturing about graphical models, which is a dream. So as I said, I'm Jeff Bilmes. We have office hours, so I will be holding office hours Mondays after class. From 1:35 to 2:35. The reason why it's 35 is because it takes a good 5 minutes before I can walk back to my office from here, at least. Maybe a little bit longer even. You can also make an appointment with me, a special appointment, and I'm also happy to meet with you on Google Hangouts or Skype or any electronic means in the evening sometimes as well. Just email me. The TA we have is John-Soup Park, who's right there. John-Soup, could you please stand up? Thank you. John-Soup will be helping me in all matters graphical model. And his office hours are Tuesdays from 12 to 2 in EEB 333. We have a web page. You should be able to go to it now, and it's live. And these slides electronically will be available, as I do for all of my classes, in multiple forms before the lecture begins. So if you have an iPad or a laptop or something, or you want to take notes on the slides, you can feel free to download them and mark up the slides themselves with additional notes. I myself am using an iPad, as you can see, to mark up the slides like this. There's our web page. So in terms of homeworks and what you'll need to do, so we'll have about 3 to 5 homeworks this quarter. You'll have about a week, maybe to a week and a half to turn them in. We'll also have sort of a take-home midterm, which I'll talk about a little bit. I've already said the copies of the slides are on the web. And also, with regard to readings, I'll say something about the readings in a minute. But most of the readings, or at least a lot of the readings, will be available will be made available on the web page itself. So you should keep track of that. Homeworks are, fairly standard. There'll be things like answering questions, which you might have had before in a homework, or maybe proving a theorem. There might also be some programming assignments. You hopefully will have known by this point in your life career a programming language like C or C++ or MATLAB or Java or something. It should be the case that most of the programming assignments can be done using any programming language of your choice, although some languages might be more difficult than others, depending on not only the language constructs, but also possibly some of the libraries that are available in those languages. And homeworks must be turned in electronically. So we are trying to make this class as paper-free as possible. So that means that you need to turn in PDF files of your homeworks. If you like doing them by hand on paper, you're still free to do so, but you must figure out a way of clearly scanning them in, turning them into a PDF file, and then uploading the PDF file. So you will keep the original paper for posterity's posterity's purposes. You can show them to your grandchildren someday. Or you can email them the PDFs. Either way, you have lots of choices in this class. There's a chance, this is the final project actually. I want to talk about the final project. So I'm not sure yet what kind of final project we're going to do. I still haven't fully thought it out. Maybe we can discuss it a little bit in class, but it will be either one of two possibilities. The one possibility, which is what I've traditionally done in this class, is basically a final presentation and a paper reading where basically every student comes up and presents a paper or a set of papers that are recent research. This is a class on advanced inference and graphical models, and so we're going to be covering some pretty intricate stuff. Therefore, once you're done with this class, you should be very well versed in the recent literature. You should be able to read any paper in NIPS or ICML or UAI on graphical models. On the other hand, since we have, I think, 28 people enrolled in this class, last counting, and somebody else wanted to enroll as well, it might make more sense to do an alternative final project, and that's sort of a programming contest. And I did this last quarter for the first time in a different context, but it might make sense to have people form groups of maybe 2 to 3 people and write code to actually do graphical model inference. And then we'll have a contest at the end of the quarter where your code will be timed, and there will be a winner, hopefully. And that sometimes is a very useful pedagogical experience for everybody. So we'll see. I haven't decided yet. Okay, also we will have reading materials. So the reading will be drawn from a number of different sources. The stuff on graphical model semantics and exact inference in graphical models will be handouts written by myself, and that they will use the same notation that we're using in class. And it will talk about things like what does it mean, what does the graphical model mean, what are families of probability distributions associated with graphical models, and how do you do exact inference in graphical models. And then we will also draw from 2 other sources, which I will talk about in the next page. And there might also be a couple of research papers that I link to from the web page, and they will be made available as we talk about it. You might also, we're not actually going to be drawing directly from this book, but there's a very nice book by Colin Friedman that has a plethora of information about graphical models, which you should, if you're interested in graphical models, own, probably. There's also this classic book by Stefan Lauritsen on the semantics of graphical models, which it's amazing to me that this book is almost 20 years old because it's still quite relevant today to what graphical models are, and some of which we will be drawing from. There's a couple of other books by Jensen on Bayesian networks, which are worth taking a look at. And then lastly, there is some discussion on graphical models in 2 machine learning books. The first one is Bishop from 2006, and the second one is Murphy from 2012. I assume that in 2018 there will be another machine learning book coming out in 2024. These things come out every 6 years, apparently. So there's only 2 of them now, so you just pick them up now before it becomes 2018. The actual books that we'll be drawing from, or at least the main books, are Wainwright and Jordan, Graphical Models, Exponential Families, and Variational Inference, which is available from a university domain for free. So you can actually go to this web page and download the PDF file of that book, which is great because it's free. The second one is from a different perspective. It's graphical models inference from a computer vision perspective, which I think is a very different way of doing certain inference tasks in graphical models, and we will be drawing from this book as well. This book, unfortunately, I can't say is available for you for free. However, you may want to pick up a copy, or probably will want to pick up a copy, because we will be drawing from it as well. Although some of the material in this book are research papers which are available in other contexts as well. So we'll see whether you actually need it. You have a reading assignment. I haven't put this on the webpage yet, but there will be a chapter called Trees, which will be how to do exact inference on trees. And we will talk a little bit about that probably starting on Wednesday, but you can get started on this very soon. I will probably be posting these things on the Canvas page. So we're using Canvas rather than Catalyst for our homework and for our announcements and for our discussion board and for postings, reading postings. These chapters that I'm going to be making available to you are not they're not published, so I will probably put them on Canvas. On Canvas, the only people who can get to the Canvas pages are myself, John Soup, and all of you. The rest of the world and the YouTube audience can't, which I realize is a problem, because if I'm making this video available for YouTube, why should I not also make available all of the readings? And this is something I haven't yet fully decided upon, whether or not I'm willing to make chapters that I've written full of typos available to the rest of the world, and I don't know yet. So we will talk about that, or we'll decide that as well, or I will decide that, I suppose. You can also, by the way, get ahead in the class. So a lot of the slides are sort of based on slides that I've previously prepared from previous times I've taught this course. The most recent time I taught it was in 2011. And there is the web page, which is still active and available, and you can actually look at some of the slides. Although the slides are being updated and improved, and typos are being removed, and every time I teach it, I always improve the class. So the most recent slides are being prepared before each lecture. Oh, I should also mention that there are a number of slides here that we won't have a chance to cover on semantics of graphical models and Markov properties. So I will, if you're really interested in this kind of stuff and some of the proofs that we were going to skip over this quarter because we need to get into some of the inference mechanisms, take a look at the 2009 offering. Okay, so every day we will look at this. We actually have 20 lectures in this class. None of the holidays fall on this quarter fall on days of our lecture because we're a Monday, Wednesday class. For some reason, is it Labor Day or Veterans Day? It's on a Tuesday, which to me, I found that very surprising. But yes, we have a holiday on Tuesday, November 11th. So for whatever reason, I will be seeing you on Monday, November 10th, and Wednesday, November 12th. But you can take Tuesday off if you want. Okay, and in terms of the slides, this is where we will have review. Okay, so let's get started. Are there any questions about the logistics? Yep.
Yeah, just about logistics in the classroom. Since it goes till 1:30, is it okay for people to bring and eat food?
Oh, that's a great question. And in fact, I was going to mention that. Yes, we are having our class right in the middle of lunchtime, which I thought isn't supposed to happen, but it happened. So feel free to bring your food and eat, but please eat quietly. Otherwise, the rest because the audio is going to be on YouTube as well, and for the rest of eternity of humankind, people will hear you crunching on your potato chips, say, which may or may not be a good thing. I don't know. Maybe if you're endorsed by a potato chip manufacturer, you would want to have such a thing, because they used to say that the crunchier the potato chip, the better it is somehow. So maybe you'd want to convey that message to the YouTube audience. I don't know. But yes, feel free to eat. But also, please go into airplane mode when you eat, because do you know, has anyone ever taken a flight and someone brings their food right next to you and starts eating, and you're like this? So since people are kind of close together, feel free to, eat as you would in an airplane, which may not be a very inviting and appealing prospect for those of you who are hungry right now. But might be mindful of your neighbor. Don't spill like purple Kool-Aid on your neighbor's laptop or something like that. That's a bad thing. Okay.
Approximately when this midterm will happen?
Approximately when the midterm will happen, it will happen approximately 10 weeks into the course. Approximately. Somewhere in the middle, the mid-quarter. Midterms happen in mid-quarter. I haven't decided the exact date yet. But since it's a take-home midterm, it's not going to be something that's in class. It will be a take-home. It'll be like a long problem set.
So it's basically harder homework. So
it's basically a homework that is impenetrably difficult and impossible to do.
Okay.
So that's right.
Homework.
Yeah. So yes, harder homework is another way of putting it. Yes.
Would midterms spent on weekdays or weekends?
It's up to you. It's up to you. I can't answer that question for each person. If you finish it before the weekend, or if you decide not to work on the weekend, then no, it doesn't span the weekend. If you decide to work on it during the weekend, yes, then it takes over the weekend. So it's up to you. So of course, depends on how many other midterms you have, and lots of other things. Maybe you are getting married the day it's due. There's all sorts of possibilities. Or you could be going for a race, or you could be going swimming, or maybe there could be a snowstorm and the class would be canceled. So lots of things could happen. So, okay, so let's get started. This is now the beginning of the actual content. And since the things that on my iPad and on the screen, everything looks fine, but on this, it doesn't. So what I'm going to do is just pause for a second and try to fix the screen, because I don't want to have to deal with, in the middle of a topic, the screen not being fixed. So just give me 1 second. Okay. So you are now on YouTube. Yes, your visage, your face, everything. So so let's talk about probabilistic inference. So in some sense, I mean, in many senses, in fact, this is a machine learning class. However, what we're going to be talking about in this class is not so much actual learning, but probabilistic inference. And probabilistic inference is a very, very important part of learning, because it involves doing things like computing probabilities that one needs based on available probability distributions, or probability distributions that maybe you wish to acquire. And very, very simply, probabilistic inference includes things like, for example, marginalization, where you have, say, a joint distribution over P of x over x1 and x2, and you wish to marginalize out one of the variables to give you a distribution, say, over just x2. Or maybe x2 is observed, x2 is an observed quantity, and you wish only to compute the maximum value of x1 for that particular observed value x2. So you might think, okay, so why do we care about doing inference? Why do we have a class devoted to doing inference? The reason why is because probabilistic inference is actually hard. And what I mean by hard is very precise and formal. It's actually NP hard, and oftentimes it's inapproximable. Sometimes it's information theoretically hard, meaning that it's exponential time. Now, you might look at this and say, well, wait a second. That doesn't look hard to me, and that doesn't look hard to me either. That's just simply summing over x1, right? Or that's just simply maxing over x1. However, when x1 is a massive, long, say, 100-element, even binary vector, then doing that summation would require 2 to the 100 terms in the sum, which would be exponentially difficult. Or similarly, maximizing over x1 would also require a comparable amount of computational steps. And so therefore, one can't naively just say, I want to do that sum, or I want to do that max, and hope that I can be able to do this in the general context. And so graphical inference is basically doing these kinds of things. Now, in some cases, and when we're going to be studying exact inference, doing this kind of thing can be done actually in polynomial time. And oftentimes, it can be done in low-order polynomial time, where even the constants of the polynomial are small. And that's great. Like, for example, when we have tree probability distributions, which we will define, then we can actually do this efficiently. And there are many, many instances in machine learning where tree distributions are very, very useful in and of their own right, meaning just for a particular problem. There are other cases, however, where trees are used as, in some sense, an intermediary representation with which you go through to solve one of these more difficult problems. And these more difficult problems is when the exact inference, computing exact probabilities is infeasible. And so approximate inference is absolutely necessary, approximate inference of some form or another. Now there are, in fact, many, many different types of approximate inference strategies. In the, how many weeks do we have of this course? In the 10 weeks of this course, we're not going to be able to cover all of them. But I hope that if we're successful, we'll be able to go through some of the core aspects of the main approximate inference methods so that you'll be able to understand any future method that comes up. Now, this slide so far has just talked about probabilistic inference. What we're going to be talking about is inference, probabilistic inference via graphical models. And graphical models essentially give us a strategy for doing probabilistic inference. And we're going to be talking about, for example, what does a graphical model mean, or what I call the semantics of a graphical model. Exact inference methods when, for certain graphical models, you can compute probabilistic quantities exactly. And also, using graphical models, you can construct various different approximate inference methods that come to you via the fact that you can use, that you're describing things with a graphical model. So the first sort of general approximation method that we will be talking about is variational methods. And variational methods started out, I think this is fair to say, that in the 90s when variational methods started appearing, it wasn't at first realized how powerful and general they are. And in fact, now we're aware that they actually encompass and cover all of these different methods, including things like the sum product algorithm, cluster variational approaches, expectation propagation, mean field approaches, and various forms of linear and conic programming relaxation strategies. And what we're going to do then is see how the variational approach gives us essentially all of these wrapped up all within one framework, which is very, very powerful and neat. On the other hand, there's sort of an alternative inference sort of paradigm, maybe, if you will, which primarily has come from computer vision, but also comes from combinatorial and discrete optimization. And that basically corresponds to things like move-making strategies. And most simply put, move-making strategies correspond to, say, taking a probability distribution and representing it as a surrogate, or using a surrogate representation, like, for example, a graph, and solving a graph cut problem, like finding a cut in a graph, which then can be, the solution to the graph cut problem can be transformed back to the original probabilistic inference problem to give you a solution. And that most strongly relates to things like binary Markov random field distributions, which are very, very prevalent in computer vision applications. But the questions we want to ask about these kinds of techniques are, for example, like, when is this optimal? When can we do this optimally? When can we do it approximately? How bad is the approximation? Do we have some sort of guarantees, some mathematical guarantees that say that if we do this, it won't be worse than a particular value or a particular lower bound? And then how can we generalize this to like a graph cut sort of, you have one side of the cut and the other side of the cut, so it naturally corresponds to binary random variables, but how do we generalize that to non-binary random variables or to potential functions that involve lots of, not just pairs of random variables? There's lots of questions that we need to ask in this kind of approach. And there are many then approaches that sort of, many generalizations that do this, like those things like alpha beta swaps and alpha expansions, fusion moves, and many other more sophisticated move-making procedures, which is sort of the general name for this kind of stuff. So we're going to be talking about this both in the context of computer vision, but maybe we'll be hypothesizing how and where it could be used for other applications as well. Like, for example, coding theory, or maybe sequential processing, or for other sorts of applications that graphical models are useful for. Now, there are other approximate inference methods as well, based on Monte Carlo methods or sampling methods, and that includes important sampling strategies. And there are also I don't want this to rotate on me. Whoops, what happened? There we go. There's also, it turns out that certain inference problems are very related to constraint satisfaction problems and SAT solvers. And there are a lot of methods based on search strategies that have come out of the field of artificial intelligence that can be used for solving certain inference problems. And this includes things like and/or search trees, which are basically data structures that actually represent the operations, the mathematical low-level operations necessary to actually do an inference problem. And so we'll be talking a little bit about these sorts of things as well. So there's a lot to cover in this class. Oh, I should also mention that beam pruning methods, which were made popular also in the artificial intelligence community starting in the 1970s and maybe even 60s, also are very related to sampling-based approaches. Okay, so let's talk a little bit about inference and learning. But before I do this, this is also a good time to pause for questions. I think it's generally a good thing to ask questions. And for those of you who have taken a class with me before, or for those of you who have never taken a class with me, I will say this to you all again, which is the following. The only bad question is the unasked question. So all questions become good once they are asked. So don't feel shy or embarrassed or anything like that about asking a question. Chances are, if you ask a question, other people in the room will have the same question, and moreover, feel some compassion towards your YouTube compatriots who will be watching this, all of these millions of users who will be watching this lecture on YouTube, who don't have the opportunity to ask questions in real time. They can't interrupt the video and suddenly ping me and ask me a question and have me answer on video. So that's something that you have an advantage of. So imagine those millions of people, maybe billions, who knows, of people. Okay, so that said, are there any questions so far?
For our YouTube compatriots, can you tell us what the prerequisites for this course?
For the YouTube compatriots, what are the prerequisites for the course? I think that I mean we're going to go fairly rapid paced, but we're going to start from the basics. So if you have a basic understanding of basic graph theory, basic probability theory, basic stochastic processes theory, maybe a little bit of information theory, just basically understanding what entropy is and those sorts of things, without actually knowing precisely all of the ways that entropy is used in communications theory, I think that that should be enough. You should also know a programming language, like C or C++ or Java or MATLAB or something. You should be a techie. You should like technology and machine learning, and you shouldn't be someone who wants to major in like ancient Albanian languages or something. But you should basically be like in an EE or a CS or a STAT or an information science or genomics or linguistics, computational linguistics department or something like that. You should have an interest in this material. Because I also think that having an interest in learning what graphical models are makes it easier. Maybe I can do a quick survey. So how many of you are here because they have an interest in learning about graphical models? And how many of you are here only because they want to satisfy some sort of prerequisite for graduation? Okay, so nobody's raising their hand. So that's a good thing. It means that everybody should enjoy this class, hopefully. So does that answer your question?
Yeah.
Okay. So let's talk a little bit about notation briefly. This is a little bit boring, but let's talk about it because it's necessary. So we're going to have a probability distribution P of x. So x in general, lowercase x is like a value of a vector of random variables. Here it's a vector of length n, which is kind of like a MATLAB notation where the subscript is an index. It's an index set of integers from 1 to n. And that's identical to the probability. It's really a multivariate probability distribution, the probability of x1 through x of n. And then very, very formally, but we won't really be writing it like this. This really means it's the probability, it's the distribution of the random variables x1 through xn of the first random variable x1 equaling lowercase x1, and so on up to the last random variable capital Xn equaling lowercase xn. So this thing here basically is our sort of, we're still not exactly perfectly in sync with what I see and what you see. But Zooming doesn't work in that case. But basically, this thing here, capital X1 is equal to lowercase x1, is really basically saying an event happened. It's the event that the random variable x1, capital X1, is equal to the value lowercase x1. So that's a very standard notation. And then similarly, if we say something like capital X of 1 through n is equal to lowercase x of 1 through n, that's the event that the vector of random variables x of 1 through n is equal to the values, the vector of values x of 1 through n. So we might have like a subset. V might be a set of all random variables. There are n of those random variables. And we might have subsets of random variables, a and b. So a might be essentially a subset of the set of integers from 1 to n. And so that allows us to sort of talk about subsets of random variables just by doing a subscript, which is the index set. So x of a, this thing here, is just this subset of random variables indexed by the set A. This is a very convenient notation because it allows us to do things like if A is the index set 1, 3, and 7, then x of A is the random variable set x1, x3, and x7. And moreover, we can talk about probabilities, like the probability of xa given xb, which would be equal to the probability of x1, x2 given x3 and x4 if it's the case that a is equal to 1, 2, and b is equal to 3, 4. So we're going to be seeing this a lot. Okay. Now, in general, a probability distribution, we're most of the time going to be talking about discrete probability distributions, but we will, on occasion, talk about continuous distributions. Things can get pretty different when you have continuous distributions because you need to also talk a lot about the particular family of density function that you have in a continuous random variable. But in the case when the random variables are all discrete, when you ask about this quantity, the probability of x of a, that, in the worst of cases, requires a table that is exponentially big, exponential in the size of a, right? And so it's r to the size of a, where r, lowercase r, is the set of possible values, or is the number of possible values that the random variable can take on. For binary random variables, r is 2. But for ternary random variables, r is 3. Okay. Lastly, we have x. You can't see that here. That's really too bad. I have to fix the screen. It's still not perfect because when I zoom in on my iPad, you see something different. But I'll try to pay attention to the screen. So x bar I and x bar j, where the I and j are in superscripts, corresponds to different samples. So we might have like a bunch of samples of random variables. For doing learning, we need to have samples, and that's the notation that we'll be using for different samples.
So the bar means a sample.
The bar basically means it's kind of observed. So it usually means that that's kind of a fixed. You can think of that as a constant throughout that set of equations that involves that notation. So it's kind of like that's not going to be varying. We're not going to take a sum over that kind of thing because it's sort of fixed. Like if you sample a coin a number of times, like heads, tails, tails, heads, tails, heads, like x superscript 1 might be heads, x superscript 2 might be tails, and so on and so forth. Okay, so what might we want to do with the probability of x? So we mentioned this before. We might want marginal quantities, like, for example, given a particular sample, compute its probability. So remember, x bar is the entire vector 1 through n. And so this is computing the probability of this multivariate distribution, the probability of x bar. That's a very simple thing to compute. Another thing that we might want to compute is we might choose some subset E, and then the remainder of E, so basically anything that we haven't chosen, let's bipartition it into F and H. So F and H is a partition of the remainder, anything that's not in E. And then we might want to compute this quantity. Hopefully you can see that. This quantity basically is to say it's kind of like a marginal distribution which sums over x of h. Here's the whole joint distribution. And so x of e is sort of fixed, right? That's kind of like an observed thing. But we want to compute the distribution over just x of f. And that would, for example, allow us to compute things like the probability of x of f given x of e, which is equal to, or I should say proportional to, the probability of x of f and x bar of e. Right, so those are the kinds of things that we might often want to compute. On the other hand, we might want to use the distribution to model the relationship between two signals, x1 and x2. Say x1 might be a feature vector. Like if you're doing computer vision, you might use SIFT features, and x1 might be essentially a vector of SIFT features, and x2 might be a class variable or a structured class variable. It might be, for example, something that indicates the label of each pixel in the image. Like, is it a chair, or is it a video camera, or is it a University of Washington student, or is it something else? And then we set up a joint probability distribution between the set of features and the set of objects that we're interested in identifying from the object. It could be an image, it could be a genome, or it could be a speech utterance, it could be anything really. And then the kind of thing we might want to do is compute probability of x1 and x2. This is in some sense the same exact thing as this, right? It's just basically making it slightly more clear that there are at least two random variables there. Alternatively, we might want to take the argmax, like given, say, x1 bar, so x1 is sort of observed, we might want to compute x2 star, right? So x2 star is the assignment to x2 which maximizes the joint probability given that x1 is fixed. Okay, and thanks to the definition of conditional probability, that's identical to doing this, right? Because it's just a constant. There's a multiplicative non-negative constant that relates the two to each other, thanks to conditional probability. Now, that's sort of inference kinds of things. Now, you know, machine learning really is some fashion of adjusting a model based on data. Right? That is maybe the simplest, highest level description of what is machine learning. And machine learning, in order to adjust the model based on data, you almost always need to do inference. And to do it practically and scalably, you need to be able to do inference practically and scalably and efficiently. Which basically means when you're using probability distributions, computing probabilities, or doing some of these inference tasks that we just saw in the previous slide. So now what is data? I mean, data is basically has the following form. We're given a set of training samples. And let's use D as the set of training samples. I'm not saying how many there are, but there's just some number of samples, and they're indexed by the superscript inside of parentheses. And then machine learning, one very, very general form of machine learning, would be basically saying, finding theta. So let's say that theta is some set of parameters that govern the probability distribution. Now, it could be, theta could be discrete, it could be continuous. We're not really saying very much about theta right now. But theta is just some set of parameters that govern the probability distribution. We're not even saying necessarily that theta is even of fixed dimensional, has fixed dimension. It could be the case that we're in sort of a non-parametric setting, in which case theta could itself span multiple dimensions. But for simplicity, let's just say that theta is fixed dimensional. And we want to find the theta that minimizes the risk. The risk is something that's a function of the data that you've got, and of course also the parameters. The risk is basically something, it's sort of like a measure of how bad theta is with respect to D and the risk function itself. And since it's a measure of badness, we want to minimize it, right? It's called the risk. And so once we've got a theta star that is optimal in some way, or maybe good, or it minimizes it, there's all sorts of things we can do with it. We could, for example, look at the parameters and interpret it in some way. This is something that's often done when one does generative models. You want the parameters to mean something, and so once you've done this learning, the parameters might be in some sense a summary of the data that you've got. The data set might be a big data set and might be hundreds of terabytes. And theta might be relatively low dimensional, that in some sense acts as a summary of those hundreds of terabytes of data. On the other hand, once we've got theta, we could actually then use it to instantiate a probability distribution, which could then be used in the future. So this is the example of learning. Like once we've learned something, once we've identified theta star, we want to use theta star in a distribution in the future for some application, like recognizing objects in visual scenes, or doing face recognition, or doing speech recognition, or doing machine translation, or doing gene discovery, or SNP identification. There's all sorts of things we might want to do. Now, what are the different possible risks? There are quite a large number of them. One possibility would be a form of generative learning, where the risk takes the form of the following. We basically take the average of the log probability of the sample, and maybe we have some regularizer of some sort. Okay, so this basically then would be, then theta is inside some norm, like it could be a 2 norm or a 1 norm or some sort of structured norm. And then lambda is the trade-off coefficient. And you can see that if we minimize this risk, we're maximizing the likelihood. We're saying that theta is the set of parameters that maximize the data, maximize the probability of the data. Okay, that's what generative learning is. A form of discriminative learning would result where we care not so much about how well the sort of joint distribution is large with respect to the data for a given set of parameters, but we care instead of how large the conditional probability is. And so this is called conditional likelihood. And this is useful, for example, for classification purposes, when our primary goal in using the probability distribution is the following, where x1 is a set of features of some object, and then x2 is, say, a class variable. And we care only about making sure that the probability of the correct class given the features is as large as possible. It's a form of discriminative learning. A third form of learning is max margin learning. And here we have a very different but equally important risk function. So here the risk function basically looks at, it's a sum over all of the data, but it's looking at the difference between the maximum penalized alternative hypothesis and the true hypothesis. And this is sort of the margin, and we're trying to sort of, in some sense, minimize the margin. Delta is like a normalizing label cost. It basically like especially in structured domains, delta is very, very important. But basically, all we're doing when we're doing max margin learning is changing the risk function, and we're still, once we've got this risk function, the goal of machine learning is minimizing theta inside of this risk function. Okay. So we have 3 different types of learning. Now, how we do this optimization for each form of risk is going to be unique. Yeah, question?
I'm just wondering what hinge loss means.
Hinge loss, so a loss is a way of judging how bad a particular sample is for the particular problem of, say, predicting what we want to predict. And hinge loss is one particular type of loss function. So there are lots of different loss functions. In fact, in some sense, here, these are 2 loss functions here. These are the log probability and the log conditional probability, and this is the hinge loss. It's just there's different kinds of losses. There's a wide variety of them. But my main point is to show that for pretty much all of these strategies, for all these different loss functions, even though doing the optimization of either equations 1.5, 1.6, and 1.7 might be different, in doing them, one needs to do probabilistic inference. So one needs to compute these probabilities over quantities like p of x, like we mentioned before. So to do learning, you almost always need to do inference. And so therefore, inference is a critical part for machine learning. And we're going to be concentrating in this class, like I said, on doing inference. Inference, by the way, I should also mention, for those of you who are interested in communications theory and coding theory, inference is how you do a decoding. Inference is the strategy that when you receive a message from some noisy channel, you've got some observations and you have some probability model which basically relates the received signal to a clean version of the signal. Inference is how you compute the decoded message with some, because it's a probability distribution, hopefully, if you do inference properly or with some sort of assurances, you've done a good job, and you have some quality assurance as to the decoded message, or some sort of fidelity associated with it. Okay, so inference, we've talked about inference, and we've talked about probabilistic inference, and we've talked about machine learning a little bit. But we haven't at all talked about graphical models. So let's say that we have n random variables, okay? And let's say this green blob over here on the right corresponds to the set of all possible probability distributions over n random variables. So that basically means like one dot in this green blob corresponds to one probability distribution. And there might be a countably infinite number of probability distributions inside of that green blob. Okay? And so U is the set of all probability distributions. It's a family of all probability distributions. Okay? Now, we might get some training data, some sample data, and we might do some optimization procedure, and we might choose an objective, a risk function like we talked about. And we then are trying to identify some p of x inside of this large blob that is close enough, or maybe exactly equal, to whatever the true probability distribution is. Now, we don't have access to the true probability distribution. We only have access to samples. But the point is we have this very, very large family, U. And from amongst this family, we're trying to identify the distribution that's close to the truth. So here's maybe the ideal distribution, the one that's closest to the true one. But let's say because it's computationally difficult or intractable, or because you have limited time or computational resource budget, the only one we can identify, the best one we can identify from amongst U is this one down there. And let's say it's a very, very poor approximation to the truth. The reason why is because there's so many possibilities. Within U, within script U, it's kind of like it's just difficult to find the true distribution. There might be a very, very difficult nonlinear optimization problem within which one can't assuredly find anything that's close to the truth. But what if we instead do the following? What if we say, okay, I'm not interested in all of you. I'm interested in a subset of you, a family, say F. And F is green. And so it's supposed to look inviting and friendly and maybe searching in some sense, or learning. Learning is in some sense kind of like searching, right? You're sort of searching for a good distribution in response to data. So searching within F, or learning within F, maybe is much, much easier than learning within U. Maybe learning within F is strictly a convex problem, for example. Or maybe there are other reasons, even if it's not a convex problem, maybe there are other reasons that, for example, identifying a point, a good point within F, is easier than identifying a good point within U. It's a constraint that while it limits the family that you're working with, it actually makes it easier to work with. So the idea is that U is too large. Okay, it's too large or too complicated. And let's say it's plagued with lots of local optima. It's very nonlinear, non-convex, and all sorts of difficult things. But on the other hand, if we restrict it to F, the actual solution, the solution that we are able to find in F, even though F is a restricted family, might be better than the solution we would find in U. Okay, so like this guy here, that's what we would find if we had an unconstrained solution, whereas this guy here is one that we find by constraining the set of possible distributions we care about. Okay, so how is this possible? So it turns out that graphical models, what is a graphical model? So this is the definition of a graphical model. A graphical model is essentially a way of providing for the specification of F, of script F. So a graphical model is a way of restricting the set of distributions in some nice, clean, mathematical, often exact, but if not exact, sometimes tractable to approximate way, such that one can find a good solution within F, and oftentimes the solution within F is better than the solution within U. So like here's an expression, here's a sentence from machine learning. Sometimes it's better to find an exact solution to an approximate problem, where the approximate problem is the restriction to F, than it is to find an approximate solution to an exact problem. So the approximate solution to the exact problem might be this guy down there. The exact solution to the approximate problem would be this guy here. And the exact solution to the approximate problem is sometimes and quite often better than the approximate solution to the exact problem, which is down there. Yeah, question?
So I have four basic questions.
Yep.
One is, if you just look at this figure, then the poor solution which is found is much closer to the ideal one as compared to...
Don't pay attention to the geometry. This may not be a Euclidean geometry. Okay. I could move the green circle over if that would make you happier. The green oval, sorry.
Okay, and then the second question is, do we learn the model F, or is it something which we specify based on the problem?
So this is a large part of what the first third of this class is about, is how does a graphical model specify F? How do we construct a graphical model to specify F? What are the different types of graphical models? There's more than one type of graphical model. Do we specify it by hand, which we do sometimes? Do we learn it automatically, which we do sometimes? There are a large number of different strategies for identifying the graph which specifies F. Now, there are other strategies for identifying F that are not graphical, right? But in this class, the way that we circumscribe this subset is by specifying a graph of some sort or another and making sure that we're clear about what type of graphical model we're using. Because like I said, as we will see, not all graphical models are created equal. You can even have two graphical models where the graph is the same, where depending on the graph rules, you might actually have a different family. So the point of this slide is a graphical model, I will say this probably many times, but a graphical model corresponds to a family of probability distributions. And a graphical model corresponds to a subset of the set of all possible probability distributions. Okay?
I have two questions. So first question is that how do you measure the goodness? If you don't know the true, even you know the true, how to measure the goodness of the
there are many, many ways of doing that. I mean, like for example, the learning problem. Part of the learning problem, remember we said that theta, the parameters could be continuous or could be discrete. Theta itself could correspond or could range over different graphs, as well as probability distributions within the family corresponding to one graph. So how do you measure the goodness? There are lots of standard ways. Like one can express it as a risk problem, but there's other ways as well. I mean, we will be talking about some of this in this class.
But if you don't know, I mean, what is the kind of the true model? How do you kind of measure how close you are to the true model?
Usually, so like I said, there's no one way. There's this thing in machine learning called the no free lunch. There's no one method that will work universally everywhere for all problems. But very, very roughly speaking, the way that this works is that you have some measure of goodness of fit to the data. So you have this data. You have samples of data. Machine learning involves data. You have data. You can't do it without data. You have some data. And then you have all these different possible points, right? Like, you might say, okay, this one fits really poorly. This one fits really good. This one really fits even better. This one fits poorly. Okay? Or if you're restricted to be within a family corresponding to a graphical model, you might have a measure of goodness of fit, where for each point in there, we have a measure of goodness of fit. Now, the goodness of fit model just says, how well do I fit the data? There's also something typically which is based on the second part of learning, is sort of like an Occam's razor type simplicity preference. We generally tend to prefer, amongst models that are equally good in terms of their fitness, more models that are simpler. There's a simplicity assumption. There's an Occam's razor assumption, and that's what a regularizer does. It basically then puts a penalty on complexity. Now, how do you measure complexity? There's lots of ways of measuring complexity. There's lots of ways of measuring goodness of fit. There's lots of ways of measuring complexity, and also you need to balance between the two. But in general, you want to minimize the badness of fit and complexity, and that's how we do it. But that's, like I said, not getting into any of the details. But it's all done using various forms of mathematical optimization. So graphical model. Okay, so here there are lots of different graphical models. So a graphical model is a way of specifying a family of probability distributions. A graphical model is a visual, because it uses graphs. Abstract, because it doesn't talk about one probability distribution talks about many. Mathematically formal, because every graphical model essentially corresponds to a set of equations and a very precise set of equations. Description of properties of families of probability distributions. There are many types of graphical models. The main ones that we'll be talking about in this class are Markov random fields, which have been very widely used in computer vision. Factor graphs, which are used fairly ubiquitously, and then also Bayesian networks. So 3 types, which there are other types as well, but we'll concentrate on these 3 types: Markov random fields, factor graphs, and Bayesian networks. Okay. Now, what we could do is what most graphical models courses do is like say, okay, here's a Bayesian network and there's an alarm network, and talk about earthquakes in Los Angeles. We're not going to do that. We're going to stay within the idea of a family. Okay.
In factor graphs, so what do the square nodes mean?
What do the square nodes? So a factor graph basically corresponds to a factorization requirement of a set of probability distributions, and so the square nodes are the factors, and then the neighbors or the neighbors of the square nodes correspond to the random variables that are involved in that corresponding factor. So a factor graph is really like a bipartite graph, where the square nodes are on one side of the bipartite graph. In this case, circular nodes are on the other side of the bipartite graph, and you can also think of them as a hypergraph. But we will talk about what factor graphs are. Each type of graphical model needs to have, like I said, a formal set of semantics or rules or Markov properties, which says how do they define a family? How do they define a family? We don't know that yet. But what we want to talk about now is most generally, graphical models are encodings of families of probability distributions. So the encodings are done via the graph. So you look at the graph, and the graph sort of says, these are the rules. These are the rules that any member of this family must abide by in order to be represented by this graph. Okay. So the rules are usually involve conditional independence properties or some sort of factorization properties. Obviously, maybe not obviously, but if you're familiar with what conditional independence is, that corresponds to a factorization property. Conditional independence is factorization. Is everybody familiar with that? Okay, so basically it means if conditional independence means probability of A comma B given C is equal to probability of A given C times the probability of B given C, that's a factorization statement about a conditional distribution. Should I write that down, or is everybody happy with that? Raise your hand if you're happy with that. Kind of, sort of. I'll write it down, okay, just in case. So it's probability of A and B given C. It's a factorization requirement, probability of A given C and probability of B given C. That's basically saying that A and B are independent given C. That's a factorization statement, which might or might not be true. But what a graphical model in some sense does is say, here's a list of factorization requirements that all members of the family must respect. So this is a really critical idea to understand. I mean, if this isn't clear, please read this idea again. So a graphical model is a set of constraints that all members of the corresponding family must obey. If you don't obey even one, you are not allowed in the club. You're not a member of the family. And the constraints are usually factorization requirements. Now, factorization is sometimes identical to conditional independence requirements, but strangely enough, factorization is more general than conditional independence assumptions. So you can actually you can specify factorization constraints that don't require there to be any conditional independence assumptions. And how that's done depends on the type of graphical model. Like, for example, some graphical models can specify certain types of factorization requirements that other graphical models can't do. Bayesian networks say different things than Markov random fields. Factor graphs say different things than Bayesian networks or Markov random fields. They're different. So they're not all factorization statements can be made by all types of graphical models. And that's why there's more of them. And in fact, many people study the semantics of how do you define new rules, or how do I define new semantics for new types of graphs. I could annotate the graph in different ways. I could use different colored edges or different squiggly lines or all sorts of things. You can, if you're formal about it and making sure that you're precise about what the graph means, then you've defined a new graphical model, new type of graphical model. Now, why do we care about factorization in general? I mean, we said that we're doing inference. In general, factorization is nice, and we will talk about this very precisely. This shouldn't, if this isn't clear to you yet, don't panic. This will become clear to you. Factorization, if it's the case that we are assured that all members of the family possess a particular factorization requirement, then we can take advantage of that computationally. We can, for example, distribute sums inside of the products and then sum over what will ultimately end up being an exponentially smaller set of different values of random variables. And you can turn exponential time computation into linear time computation, amazingly enough, thanks to the factorization. So factorization is really, really critical for doing computational operations on families of probability distributions. Now, we need a little bit of graph theory. But I do, since this is a 2-hour class, I usually like to take a break. So why don't we, first of all, pause, or before we pause, let me ask if there are any questions. Raise your hand if you have a question. Raise your hand if you were frightened to ask a question.
Other than graphical model or any other families or framework you believe kind of important, what's the kind of comparative other alternative framework we also maybe consider in other classes?
Yeah, there's another, so the question is what alternative frameworks for expressing constraints over families of probability distributions might there be? So usually they take the form of manner restrictions. So they don't, for example, like involve factorization, but there are some other sort of ways in which the random variables can relate to each other, even if they're not broken into a set of factors. And that's an active research area. You should have taken my class last quarter if you were interested in that. But I don't want to say the word. But okay, are there other questions? In this class, however, we're going to be the forms of restrictions we're going to be based on. They're going to be graphical. That's graphical models. Questions? Yes.
So, like, you could have the same graph picture, but then if you enforce different, like, whatever conditional independence, it would just be a different graphical model in the way you're describing it.
Yes. You could potentially have different the same graph with different ascribed semantics, and it would be a different family. So when you have a graphical model, you have to be precise about what are the allowable set of graphs, number one, and also what is the meaning of that allowable set of graphs, the meaning, the semantics, and which are, again, these formal mathematical precise rules, if you will, that say what constraints does this graph impose with respect to the semantics. I have some notation for this in a minute. We'll talk about this. It's not a standard notation, but I think it actually is a nice notation because it avoids confusion when you're learning about what a graphical model is. Because a graphical model doesn't say anything, it doesn't necessarily instantiate it down to the particular distribution. You need, in addition to the graph, you need, say, the parameters or something else to say, okay, well, the probability of heads is 0.3. You need something else to actually get the probabilities in addition to the graph. You need the numerical or other sorts of parameters. But we will make this precise. Yeah, question?
So my understanding of factorization is encoding dependence or conditional independence. So are there any other information can be encoded by factorization?
Yes, there's, as I mentioned a minute ago, that factorization is more general than conditional independence.
Can I give
So,
an example?
can I give an example? I can give an example, but I can give you an example now, but I want to pause for a break. But let's say I've got a factor graph. I mean, the things I wanted to talk about these different families, but I will give you the example, and then let's come back to it maybe at the end of the lecture. So consider this factor graph. So there's 3 factors, and 3 random variables, x1, x2, and x3. So factor 1 involves x1, x3, factor 2 involves x1 and x2, and factor 3, say, involves x2 and x3. So that's a factor graph. So if I were to express this distribution, it would be something like probability of x1, x2, and x3. Now it's not arbitrary. What it says is that it has to be representable as phi of x1, x2, where that's one factor, times phi of x2, x3, times, can you see what I'm writing? Yeah, phi of x3 and x1. Okay, my claim is that while this graphical model expresses constraints, which basically says that any member of the family must be representable by this. By the way, I should make this a little bit clearer that these are different functions. This is phi 1, 2, phi 2, 3, and phi 3, 1. So these can be different phi functions. Okay. The constraint expressed by this graphical model is that any member of the family must be expressible in this particular way. Okay, meaning that there's no phi of x1, 2, 3. There's no ternary factor. This is a distribution which has no conditional independence properties. However, it's still constrained. It's still not all possible distributions because there's no ternary factor. So it's a graphical model that expresses factorization that isn't a conditional independence property. Okay, but when we get into the different semantics of these, we'll see examples like what sometimes Bayesian networks can do stuff that MRFs can't do, and we'll see some other examples. So we're getting a little bit ahead of ourselves. But let me just pause now because people might need to take a break. I mean, you've all been standing for a very long time now, and you might want to rest. And the YouTube listeners also, they've been glued to the screen for the past hour. Now they might want to pause. So, all right, let's take a short break. Okay, so we wanted to define, first of all, welcome back. We wanted to define a little bit of graph theory, so let's erase this stuff. Okay, let's talk a little bit about graph theory. Question?
Is it possible for two different models to describe the same set of family distribution?
Yes.
Okay, so it's like, I'm not talking about like an MRF or a Bayesian network, but it's like it's the same type of model, but they just look different connections.
Yes. Those are called Markov equivalent graphical models, or Markov equivalent graphs. And there are many examples. The ones that immediately come to mind are in the context of Bayesian networks, where if you have any model that has the same V structures, namely the structures that have edges going into a node, so you can change everything up to the set of V structures and you'll have the same family. So oftentimes when you're doing structure learning, you care about learning the equivalence class more so than you do about the, which specific point within that equivalence class do you have. So, okay, so a graph. Today we're really going to be talking about undirected graphical models or Markov random fields. I think they have the simplest semantics, and they're also widely used in computer vision. So we start with a graph. So G is a graph which consists of a pair of vertices. So V is a set of vertices, and E is a set of edges. So vertices and nodes are used interchangeably, and the edges is a subset of the Cartesian project of V and V, right? So basically, you can say, for example, that if I and J are two vertices, then whenever you say that this is true, the pair IJ is in E, then that means that I and J are connected. So if this becomes I, this is X of I, and this is X of J, then these guys are connected. That means that edge exists. And this edge is called IJ. So it's typically the case that nodes are in one-to-one correspondence with the vertices of the graph. And so basically, there wasn't, it wasn't sheer coincidence that we used uppercase V as the index set of the random variables in the notational slide that we had a couple of slides ago. In fact, V also corresponds to the vertex set of the graph. And x of V then is the complete set of random variables. Okay? And then x sub lowercase v, where v is one element in V, here corresponds to one random variable. Now, there's nothing, this is important, there's nothing that absolutely says that x of v, this x of v here, has to be a scalar random variable. X of v could itself be a vector as well. But the atomicity of the graphical model is that you don't say anything further about x sub lowercase v. X sub lowercase v is just sort of either a scalar or a bundle of variables, information of which you have nothing about. Like, for example, does there exist any subsequent or sort of additional set of independence properties amongst those? So you just have to assume nothing about x of v if x of v, if this little x of v, x of little v happens to be a vector. Okay, these are called habits, starting good habits early. This is why I say these things. Okay, so a graphical model describes a family of distributions over x of v. And along with a graph, there exists, when specifying a graphical model, a set of rules, or maybe a better term is properties, or often called Markov properties, that help to define what the graphical model means, or that actually are necessary to define what a graphical model means. And so here's the notation that we're using in this class for that. So basically, before we just said f is a subscript of u. Now we're saying f, which in some sense is parameterized by the graph G and a set of Markov properties M, is a subscript, is a subset of U, the universal set of all distributions. Okay, so basically if you change either the graph or you change the Markov properties, you may get a different subset or subfamily F. So then when you look at f m g of m, this thing, any member of that, so f is a family of distributions. Maybe it has only one distribution in it. Maybe it has an uncountably infinite distribution, set of distributions in it. But the point is that any member of it must obey the constraints that are given by the graphical model under those Markov properties. Okay? And any distribution that even violates one constraint is not a member of the family. So like I said before, in a graphical model, the constraints take the form of some form of factorization, and oftentimes which are conditional independence assumptions. We're going to see examples of these in a minute. And as also I said before, factorization is useful for computational reasons. And I didn't mention dynamic programming, but dynamic programming is essentially the strategy, is the mathematical strategy that takes advantage of distributing sums inside of products to reduce computational steps. Now what's nice about a graphical model is the following. It's not always obvious how to do the optimization optimally. How to compute probabilistic inference optimally. But what one can do oftentimes, and this is sort of the power of graphical models, is the following. One can just look at the graph and the Markov properties and deduce a strategy for computing probabilities just for that graph and the Markov properties. And you can sometimes do that optimally. And once you've done that, that means that you've got an optimal inference strategy for all probability distributions in the family, even if it's the case that the family contains an infinite number of distributions. So the idea is essentially one of amortization, that you work with the graph and the Markov properties, you come up with a strategy for doing computation, and that allows you to operate on any member of the family. So that's a very powerful idea, very powerful computational idea.
Can we see Markov property is more general than the conditional probability, since the factorization is kind of associated with a definition of FGM, then it means that the markup property is equivalent to factorization, and that is more general than the definition of property.
Yeah, I think, so we're a Markov property, if it allows one to specify factorization, since factorization is a generalization of conditional independence, yes. The answer to that question is yes. On the other hand, Markov properties often can be specified as conditional independence properties, in which case it's not a generalization. But there are different types of Markov properties. We will see some simple ones today, because I think this will give you an idea. So each type of graphical model requires a certain type of graph. For example, some require a directed acyclic graph, or a DAG, and like a Bayesian network requires a DAG. And there are Markov properties associated with them. Like there's the notion of D-separation. But there's other Markov properties associated with Bayesian networks as well. So a graphical model really is a graph. It's a pair of a graph and, in some sense, a required set of Markov properties. And the Markov properties tell you what the graph actually means, or how does the graph carve out a family. Without the Markov properties, you can't know how the family is carved out. So here's sort of a conceptual picture. So we're using this notation, I guess this notation here, a little bit loosely. So it's not like F is functionally related to M in the sense that you plug M in and you get this function. We're, in some sense, instead sort of naming the family with the Markov property. So we're using it more sort of as a name specification than, say, sort of a mathematical functional expression using this notation. So, and here's what I mean by that. So let's say that R is, you can think of R as like one property within M. So this is only a conceptual picture. So R is a member of M. So M is a set of rules or something, or properties or something. And you can think of it as a predicate. So it's a true-false predicate. It's a rule. It says, okay, here's R is a member of M, and I've got some probability distribution, P, and some graph G. And the question is, does probability distribution P respect the rule R under graph G? Yes or no, or true or false? Okay? So that rule, which is part of, is one of the Markov properties, can be either violated, in which case R of PG is false, or it can be correct, in which case R of PG is true. And so that means then we can conceptually specify what a graphical model family is the following. So this family is basically the set of all distributions P, such that P is a distribution over this set of random variables, number one, and RPG is true for all members of M. Okay, so that's really conceptually what we mean by this family. And again, we have that this is necessarily a subset of U. It could be the case that it's equal to U. You could specify a graph that specifies no constraints at all, in which case you haven't done anything really. But usually that's not the instance that you care about. You want the graphical model to give you a subfamily because working within that subfamily has some attractive, beneficial, computational, or nice property itself. Yep.
So is there so we develop these inference mechanisms for a particular graph with certain Markov properties and graph structure and everything.
Yep.
So, but if you are given a new graph, you might have to verify that all these properties are being satisfied. But that may itself be potentially very hard. Right?
Yes.
Sometimes.
Yes.
So then, what is it that there's something missing there?
Yeah, it's not that there's something missing. It's that that's a great question actually, because there are areas where one is, for example, trying to find the minimal way of essentially specifying a Markov property, such that, like, for example, this I mean by computation. But what I mean by this being conceptual is that it's not as if, say, M is a massive list of properties, and when a new graph comes along, you'd go through this list and make sure every one of these properties is true. And in fact, in some cases, one can show that you have an exponential number of things that need to be specified. Like, for example, conditional independence properties themselves. Sometimes you would need to specify an exponential number of predicates. You need to verify that. Instead, however, what one can do is when one is talking about a family, one can prove theorems about certain properties being equal or not. And you can still verify these properties. And the graph itself, the graph can actually represent an exponential number of conditional independent statements. And just by instantiating families based on the graph, you have sort of automatically verified that by proving a theorem. So the theorem ensures that those properties are all verified, even though operationally one would never do anything like this. That's what I mean by this is sort of a conceptual definition, not really an operational definition. So one wouldn't. But I think conceptually it's very useful because in some sense that's what a graphical model is. It's basically a set of constraints that all have to be satisfied of members of the family. So here's saying the same thing. So basically any P, which is a member of this family, satisfies all the rules. So if you take anybody who's outside of there, so U except for the family, so this backslash notation is set subtraction. So if you take any this guy, if you take any P that's not a member of the family, there has to be at least one property which is violated, one or more. Right? So it means that you're not a member of the family. So you can think of M and the graph as kind of like a filter. So let's say U is the set of all distributions, and here's sort of a funny little picture that says, okay, this family is specified by the graph, which in this case says that there's 4 random variables. The graph is a cycle, it's a 4 cycle, and there's a set of Markov properties, M. And it carves out this subfamily. So what, at least conceptually, this is again thinking about this conceptually, what might this mean? So if we take a particular R in M, that might be the following. It might say something like, if you are 2 nodes, U and V, and those 2 nodes are neither directly with an edge or indirectly via a bunch of other nodes connected via a path, then it must be the case that any distribution that is a member of this family must have it be the case that the 2 corresponding random variables are marginally independent. That would be one possible rule, conceptually. Now, the kinds of questions, and if we were studying formal graphical model semantics, and like I said, this class is really more about inference, but if we were studying graphical model semantics, we might, for example, ask questions about these properties. Like, for example, can the property set M be listed in finite space and computed efficiently? Sometimes, yes. I mean, it really depends. We will see. It also depends on how we've specified these properties. But yes, in general, it can, and we're going to be doing that in a minute. So for a given type of graphical model, are there more than one set of rules that define a family? So in other words, is it the case that M1 and M2 are distinct, but it's the case that for all G, these 2 families are identical? Yes, that can happen. Doesn't always happen, but it can happen. So this book by Lauritsen in 1996 is primarily about this aspect of graphical models. And there's very little in the way of computational strategies for dealing with graphical models in that book. It's more sort of, what do graphical models mean? Okay. Yep.
Another general question. In this class, will we be only looking at estimating the parameters of the graphical models, or also going from data to the structure of the model?
That's primarily what we're going to be doing. It's going from data to the graphical model, structure and parameters.
So the corollary to point 2, if we were to keep M the same and change G, say G1 or 2 different Gs for a given M. Yes. Would that also be?
Yeah, that can happen too. So that was Chandrasekhar's question from before. That you can have Markov equivalent models. That for the same M but 2 different Gs, you can actually have the same family. That can also happen. So we can talk about Markov equivalence, where we have F of G1 and M is equal to F of G2 and M. So the definition of Markov equivalence, 2 Markov equivalent graphs would be ones that this is true. So what I like about this notation is even if it's sort of informal and conceptual, it allows you to sort of formally define Markov equivalence in terms of the families being identical. Okay. So here's the other kinds of questions we might ask. So is there a smallest rule set? So all the rule sets say M1, which is a subset of M2, such that like we have redundant rules, and we don't want to have these redundant rules, extra rules. Yeah, that's also possible to happen. And then if there are redundant rule sets, then is it possible that we can identify the smallest m such that that's all we need? So that's a tricky question. Sometimes that can be a very, very non-trivial question to answer. That requires sometimes pages of mathematical proof. Simple question, hard answer. Are there rule sets that are non-equivalent? Well, this should be clear, right? For the same graph, you have different rule sets that specify different families. Yes, this can happen too. So like I said, much of graphical model theory is deducing properties of these rules and the corresponding properties of graph. And novel graphical model theory is, for example, developing new types of graphs and new types of rules and semantics and saying how they are usefully describing subsets of probability distributions. So we're not going to get too much into this, but we should certainly be aware of it. Yeah? Question?
What was the answer to the first one? Is there a smallest rule set?
There can be, but like I said, other times it's very difficult to find it. But to show that it's the smallest rule set is very tricky. It's a non-trivial problem. Yep.
Is there any concept about one set of rules is simpler than the other? Because previously we talked about if we compare with two different models, if their power is the same, we try to choose a simpler model. But so in this case, will there be a concept of a simpler set of rules than the other set?
There could be. That's a very good question. I mean, there's simplicity associated with a graph, and there could also be simplicity associated with a set of rules. That is, simplicity could be measured in this particular case based just purely on size, but that doesn't. You could have really long rules, but few of them, or really short rules, but many of them. I mean, it's a measure that one would need to specify here. That's an interesting question, but certainly one could think about that. And then finally, when you think about the space of all possible graphs, you have you're sort of unioning over all graphs for a particular set of Markov properties. And so this here corresponds to the family of all probability distributions over n random variables that that particular type of graphical model under that particular set of Markov properties can represent. And moreover, you could then union over different numbers of random variables, and then you get the space of all possible probability distributions over any number of random variables that are representable by that set of graphical models. Now, you might think that equation 1.10 is always everything, but it's not necessarily everything. So there's sort of universality of the graphical model, like how much can you cover, or trivially can you include everything in a graph, but maybe there are certain sub-pieces that you can't include. The kinds of things that you want to discuss here are things associated with the specificity of the model. Like maybe you could have a probability distribution which has certain properties which doesn't violate the requirements of some other thing, but the other thing doesn't really allow you to delineate the properties of this one distribution that you have. And that's why we have different types of graphical models, because some kinds of graphical models, like for example Bayesian networks, allow you to delineate a particular type of requirement that maybe other types of graphical models, like Markov random fields, don't allow you to delineate. Okay, so like for example, these are just some notational examples. This would be the family of all distributions that are describable by a Markov random field. This would be the family of all probability distributions that are describable by a Bayesian network. Okay. So what this means is that we might have subset relationships, that maybe a Bayesian network is bigger in the sense that the family is bigger, or we might have family containment, or we might have the Bayesian network is smaller. And it might depend very much on the graph. Of course, the graph, the corresponding graph, since a Bayesian network requires a directed graph and a Markov random field requires an undirected graph, would need to be changed as well. But we will see, like for example, with this framework, you can, if any of you have, for example, understood the idea of moralization, we will use this type of notation. It will make, I think, the process of moralization in a Bayesian network just incredibly clear to you. So I think that the reason why I think you will like this notation and this notion soon. Okay, so let's do an example. So what is then graphical model inference? Well, we already saw these examples before. So what a graphical model inference is based on just the graph and its Markov properties to deduce a strategy for computing any of these kinds of quantities. Okay. And we are interested in doing this, and oftentimes what we can do is understand the computational complexity of computing these quantities purely based on looking only at the graph and the Markov properties. Like for example, here's a family of probability distributions. Can I do this argmax for any member of the family in this family? With the graph, you could prove that no, you can't do this unless you pay exponential time, or you can do it, or you can maybe approximate it for any distribution in the family. And so graphical model inference is more specific than probabilistic inference. Graphical model inference is using the graph usefully to help you do probabilistic inference procedures for members of the family associated with the graph. Okay. And so this is, like I said before, an amortization property. So basically, we can amortize. We amortize the work done. I have a feeling that the clock on the wall is a little bit slow. So it sounds like we're having another class coming in. So let me just end with this slide here. So what do we do with a graphical model? We have a graphical model and a family, and maybe that's designed by some person there. And once we have that, we would just look at the graph and the Markov properties, and we would design a graphical model inference procedure. Now this inference procedure can work for any member of the family. So now we've got an inference algorithm. And then we have some member of the family come in, right? And maybe we have a particular probabilistic query and some data, and hopefully, we get the correct answer. So this is the idea of the amortization, that this process here is done without ever looking at any particular distribution. And like I said, this makes this idea very, very powerful and useful in many machine learning contexts. Are there any questions? Okay, that is lecture 1. Thank you very much.